Okay, let's get into this. You know, when we think about textile waste, the scale is just staggering, isn't it?
It really is. Huge amounts piling up in landfills or being incinerated.
And the recycling rates are tiny, like less than 1% actually becomes new clothing of similar quality. It's a massive problem.
Yeah, and one fiber that's really common and also tricky to recycle is viscose.
Ah, viscose. That soft, flowy material a lot of clothes are made from?
Exactly. It's a man-made cellulose fiber. Super popular for its comfort, but it comes with challenges.
Right. You said tricky to recycle. Why is that?
Well, the standard methods we have, they tend to break down the viscose fibers too much when you try to recycle them from old textiles. You lose quality.
Okay, so that's one problem. Difficulty recycling the fabric itself.
And then there's the production side. Making virgin viscose, traditionally from wood pulp, uses some pretty harsh chemicals.
You mean like carbon disulfide,
Yeah.
CS2?
Precisely. CS2 is effective for the process, but it's toxic. There are significant environmental and health concerns, so the industry is really looking for ways to use less of it or none at all.
So we've got this popular fabric, hard to recycle well, and its production involves this problematic chemical.
That's the crux of it, and that's exactly what the research we're diving into today tackles head on.
Okay, so we're looking at a specific study.
Yeah, a paper by Forsberg and colleagues published in Sustainability just this year, 2024.
And what was their main goal with this research?
They basically had a two-part mission. First, could they actually take discarded viscose textile waste and turn it back into good quality viscose fiber? Is it even feasible?
Right. Can it be done effectively?
And second, crucially, could they figure out a way to do that recycling process while using less of that carbon disulfide, making it cleaner, more sustainable?
So tackling both the recycling and the chemical reduction aspect, that sounds ambitious.
Definitely. It's a really important piece of the puzzle for a more circular textile economy.
Okay, before we get into their method, maybe just a quick refresher on how standard viscose is made, just for context.
Sure. So it usually starts with cellulose, typically from wood pulp.
And then chemicals get involved.
Right. You treat the pulp with strong sodium hydroxide, NaOH, that's an alkali. Then you add the carbon disulfide, CS2.
And that changes the cellulose somehow.
It reacts with the cellulose to form something called cellulose xanthate, which is actually soluble.
Soluble, okay. So it dissolves.
You dissolve it to create this thick honey-like liquid. That's the viscose dope.
The dope. Got it.
Then you push or extrude that dope through tiny holes, spinnerets, into a chemical bath.
And that turns it back into solid fiber.
Exactly. The cellulose regenerates into fibers as it solidifies in the bath. That's the basic process.
Okay. So you mentioned earlier that recycling viscose textiles using this process is harder than starting with wood pulp. Why the difference?
It really comes down to the cellulose molecules themselves. In a finished viscose fabric, those cellulose chains are already shorter than the ones in the original wood pulp.
They've already been processed once.
Right. They have a lower molecular weight. And the standard viscose process, designed for those longer wood pulp chains, tends to break down these already shorter textile chains even further.
Ah, so you're starting with shorter bits, and the process chops them up even more. That sounds like a problem for quality.
It is. If the chains get too short, the fibers you make just aren't strong enough. You don't get that high-quality feel or performance comparable to virgin viscose.
Makes sense. Plus, I guess finding alternatives to using virgin wood all the time is important anyway.
Absolutely. There's competition for wood resources, and making pulp is energy-intensive, so using recycled textile feedstock is a big goal.
Okay, so these researchers, Forsberg et al., they started with discarded textile. What kind exactly?
They used undyed pre-consumer viscose fabric.
Pre-consumer, so like scraps from making clothes, not old worn-out stuff.
Exactly. Clean waste from the factory floor, offcuts, that kind of thing. No dyes, no wear and tear yet.
And what was the first thing they did with it? Did they have to chemically treat it?
Actually, no. They kept the initial steps purely mechanical, just shredding the fabric, mixing it with water, stirring it up, agitating it, and then spinning it in a centrifuge to get rid of excess water.
Pretty straightforward physical processing. No extra bleaching or harsh chemicals there.
Nope. They specifically avoided that, according to the paper, to keep the environmental footprint as low as possible right from the start.
Smart. And did starting with this textile waste lead to any immediate process changes?
Yes, quite a significant one. They found that because the cellulose in this discarded textile already had that lower viscosity, that lower molecular weight we talked about, they could completely skip the traditional aging step.
Oh, right. Aging. Isn't that where you deliberately let the cellulose from wood pulp break down a bit under controlled conditions?
Precisely. You need to do that with wood pulp to get the viscosity right for the later steps. But here, the textile waste was kind of already aged in a way.
So no need for that step.
What?
What's the benefit of skipping it?
Well, it saves a lot of time, for one, and energy. But maybe more importantly, it avoids more degradation of those already shorter cellulose chains. You preserve the quality you have.
That seems like a really key finding right off the bat. Less processing, less damage.
Definitely a win. So they had this mechanically treated textile pulp ready for the chemical part.
And this is where they started comparing different approaches.
Exactly. They focused on that first chemical step, the treatment with sodium hydroxide, the alkali. They compared the standard method, what they called single steeping, or SS,
Okay, single steeping.
with a modified version they called double steeping, or DS.
Double steeping. Okay, what's the difference?
Single steeping is just like the standard process.
Yeah.
You soak the cellulose in a strong NaOH solution once. Pretty simple.
Right.
For double steeping, they added a second soaking step after the first one. And importantly, this second soak used a weaker NaOH solution.
A second weaker soak. Why do that? What were they hoping to achieve?
According to the paper, there were a few potential benefits. One, maybe reduce the total amount of NaOH left in the system. Two, perhaps get the cellulose fibers to swell up more, making them react better later.
Okay.
And three, maybe wash out more of those unwanted bits, the very short cellulose fragments or other impurities that can mess up the process later on.
I see. So potentially cleaner, more reactive material going into the next stage.
That was the idea. And this steeping, whether single or double, happens before the critical step with carbon disulfide.
Right, the xanthation step using CS2.
Yeah.
And this is where they tried reducing the amount.
Exactly. This was central to their experiment. For both the single and double steeping routes, they tested different levels of CS2. They used the standard industrial amount, which is about 36%.
Okay, baseline.
But they also tried much lower amounts, specifically 19% and 25%.
Ah, so the big question was, could that double steeping method make it possible to get away with using less CS2, like 19% or 25%, and still end up with a usable viscose dope?
Precisely. Could DS compensate for the reduction in that key, but problematic chemical?
Let's look at the results then. What happened with the standard single steeping method when they used this recycled textile? First, with the high CS2 level, the 36%.
With 36% CS2, the single steeping worked reasonably well. They managed to produce a viscose dope.
A usable dope, like one you could potentially spin fibers from.
Yeah, the properties looked okay. They measured things like the filter clogging value, that's called the KR value, and the gamma number, which indicates how well the CS2 actually reacted.
And those values were decent.
They were comparable to what you'd expect from dope made using virgin wood pulp, so technically processable.
Okay, so SS can work with textile waste, but the catch is it still needs that full whack of 36% CS2.
Exactly. It doesn't solve the chemical reduction problem.
Right. So what happened when they tried the simple fix? Just cut the CS2 down to 90%, but stuck with the single steeping.
Well, that didn't work out so well. The data showed it was pretty much a failure. The KR value, that filter clogging number, it went through the roof. Over 4,500, which is terrible. It means the dope was full of stuff that would clog up the filters immediately, basically unspinnable.
Yikes.
And the gamma number was low, showing poor reaction with the CS2, and they found a huge number of undissolved particles floating around in the dope.
So just slashing the CS2 in the standard process with this material is a non-starter. The reaction just doesn't happen properly.
It seems the material prepared with just single steeping isn't reactive enough to cope with that much less CS2. The resulting dope was just too messy, not homogeneous.
Okay, so enter double steeping. Did that second weaker soak actually change the material going into the CS2 step?
It did seem to have an effect. They measured the alkali cellulose after the steeping, and the DS samples had a lower concentration of NaOH and slightly less cellulose overall compared to the SS samples.
Which suggests?
It suggests that the second steep did wash away some material, potentially those low molecular weight fragments and impurities they were targeting.
Okay. And crucially, did it damage the remaining cellulose? Did the viscosity drop?
No, that was important. The viscosity didn't decrease significantly, which confirms the second steeping step wasn't causing major unwanted breakdown of the cellulose chains.
Good. So the material was maybe cleaner, but not degraded. Now, the key test. How did double steeping perform with that low 19% CS2 level, the one that failed miserably with single steeping?
This is where it got interesting. Double steeping with only 19% CS2 performed much better than single steeping with 19% CS2.
Really? How much better?
Significantly. The Kr value, the filter clogging, was way down around 2100 instead of over 4500. Still not perfect, maybe, but a huge improvement.
Wow. And the undissolved particles.
Also drastically reduced, around 65,000 particles compared to over 171,000 in the SS 19% sample. Much cleaner dope.
That's a massive difference in processability. So even though the amount of CS2 was still low, and the gamma number probably reflected that?
Yeah, the gamma number was similar to the SS, 19%, indicating the CS2 amount still limited the extent of the chemical reaction.
Right. But the double steeping somehow made the reaction that did happen more effective, or made the resulting dope more uniform.
That seems to be the case. The preparation via DS, perhaps by swelling the fibers better or removing those inhibitors, allowed the limited CS2 to react more evenly, leading to a much more homogeneous and filterable dope.
So DS clearly helped make the material more forgiving, even at very low CS2 levels. What about the intermediate level double steeping with 25% CS2?
That turned out to be the winning combination.
The sweet spot.
Exactly. The DS method using 25% CS2 produced a really high-quality viscose dope.
How good are we talking? Comparable to the original standard method.
Yes. The Kr value was excellent, down around 1025. That's very similar to the value they got for the single steeping method using the full 36% CS2.
Okay, great filterability. What about particles?
Also very low, around 41,000, again, right in the same ballpark as the SS 36% sample. And the gamma number was higher too, around 33, better than the 19% CS2 samples.
So essentially, by using the double steeping pretreatment, they could use only 25% CS2 and get a dope that was just as good in terms of processability as the standard method using 36% CS2.
That's the headline result. They achieved comparable dope quality suitable for spinning, but with significantly less carbon disulfide.
And how much less are we talking again? From 36% down to 25%?
That works out to a 30.5% reduction in the amount of CS2 needed.
Wow. Nearly a third less of a toxic, hazardous chemical. That's a really substantial environmental and safety benefit.
It absolutely is. Making viscose production cleaner is a major goal, and this shows a practical way to make significant progress with recycled feedstock.
And did they mention any other benefits of using less CS2?
Yeah, the source notes that higher CS2 usage tends to create more unwanted chemical byproducts, like something called sodium trithiocarbonicate. You actually see it as an orange color in the dope sometimes.
Oh, okay.
So using less CS2 likely means a cleaner reaction overall, fewer side products to deal with.
Okay, so they found a way to make a high-quality dope from recycled textile using almost a third less CS2. That's fantastic. But the ultimate proof is in the pudding, or in this case, the fiber. Did they actually spin fibers from these dopes?
They did. They took the two best candidates, the standard SS dope made with 36% CS2 and their optimized DS dope made with 25% CS2, and they spun fibers from both. Yeah.
How did the final fibers measure up? Were they actually any good?
Yes. They tested the mechanical properties, things like the fiber thickness, linear density, how strong they were, tenacity, and how much they could stretch before breaking elongation.
The key quality metrics.
Right. And the results showed that the fibers spun from the recycled textile using their optimized double steeping low CS2 process, DS 25%, had properties that were comparable to standard viscose staple fibers.
Comparable to fibers made the traditional way from virgin wood pulp.
Exactly. They reported typical values, linear density around 2 dtex, dry elongation somewhere between roughly 11.7% and 16.4%, and dry tenacity around 14.8 to 15.5 cntex.
So basically, they made standard quality viscose fibers.
Pretty much. Solid, usable fibers demonstrating the process works end to end.
Did they note any small differences?
They did mention a slight difference in the elongation between the fibers made from the SS 36% dope versus the DS 25% dope. They speculated it might be related to the tiny differences in particle content they saw in the dopes earlier, as sometimes particles can affect the final fiber structure, but overall the quality was definitely there.
This is really impressive work. It ties together a few key achievements.
Yeah, firstly, demonstrating that this pre-consumer viscose waste is a perfectly good raw material.
And that simple mechanical prep is enough to get started. No harsh pretreatments needed.
Plus, realizing they could skip that whole energy-intensive aging step because they were starting with textile waste.
Right, and then the big one. Developing and proving that the double steeping method allows for that significant 30.5% reduction in carbon disulfide use,
while still producing high-quality viscose fibers at the end, comparable to virgin material.
It really feels like a concrete step forward. You can see how this could lead to a genuine circular system for viscose, taking waste, processing it more cleanly, and making new fibers.
It provides a clear, scientifically validated pathway, at least for these cleaner, pre-consumer waste streams. It shows the potential is real.
Absolutely. So this deep dive really highlights that potential, taking clean factory scraps, turning them back into high-quality fibers with much less reliance on a harmful chemical.
Which brings us to a final thought, really, for you listening. If this research successfully maps out a way to do this for pre-consumer waste, what does that mean for the next big challenge? Tackling the huge volumes of post-consumer viscose waste, the actual old clothes people have worn?
Right. That's a whole different ballgame, isn't it? You've got blends with other fibers, dyes, finishes, maybe contamination.
Exactly. So, building on what the study achieved, what further innovations do you think are needed? What are the next hurdles maybe hinted at in the source, like dealing with blends or dyes that need to be overcome to truly close the loop and make viscose fully circular on a global scale? Something to mull over.